This is Dr. Lewis looking at another reaction which demonstrates the effect of resonance and the sort of thing that might come up in the exam. And if you look at previous exam papers, the similar sort of question has come up. So it says, given mechanism, that means a curly arrow mechanism, to account for the reaction, and it says involving a allylic cation. So that's a clue that the mechanism at some point must have an allylic cation. That means a double bond and then a plus charge next to it. And include resonance structures with curly arrows in your answer. And why is this the major isomer under these conditions? So we've got bromination, and it's high temperature. And here we've got a dibromo compound in which the two bromos are far from each other and both are on the secondary position, whereas here this product, the minor product, it's in a tertiary position. So a high temperature, that should tell you that thermodynamics will control things, as in the most stable product will be favoured, and you would imagine that would be where you've got less steric crowding, steric hindrance between the two bromines. And also here you've got a tetra-substituted double bond as opposed to a tri-substituted double bond. So thermodynamics definitely favours this product. So what about the mechanism? Well, it says a allylic cation is favoured. But the mechanism still involves a bromonium ion to start with. So we've drawn our two double bonds, and we've got doesn't matter which one we put it above. So remember, the curly arrows for forming a bromonium ion are rather complicated. So one bond, the pi bond from the double bond goes and forms one sigma bond to the bromine. The lone pair forms the other bond, sigma bond, and you kick off Br minus. So whether the electrons really do that, that's a sort of accountancy way of showing how the various bonds are formed and broken. So we're going to form a three-membered ring bromonium ion. And we've got a double bond here. And we've got Br minus kicked off. Now there's an alternative mechanism where this gets ring opened directly, but in this question I said involve an allylic cation. So because we've got a strained bromonium ion, that can ring open, and especially if the ring open product is a resonance stabilised cation. So this is where we're going to get the allylic cation. So we've got a tertiary carbocation in resonance with make sure I don't chop off the end of it. So the double bond shifts into there, we've got a positive charge there. So we've got a resonance stabilised carbocation, and the positive charge is delocalised, so some of it's at this tertiary position and some of it's at the secondary position at either end of the allylic system. Now at low temperature, kinetics is favoured, so that means the fastest reaction is favoured, and that's the one where the most positive charge density is, if you like, if you can call it positive charge density. The highest positive charge is here, therefore the greatest coulombic attraction between bromide will be at that position, so that'll that will be the kinetic product when it reacts there. And also, and this is the position which is favoured thermodynamically, but it has less positive charge because it's a secondary carbocation. So I can show the two positions being attacked. So now we've got the minor product in this case, and it is a bit confusing with the curly arrows for resonance, but that's just showing resonance in that case. So here we get attack at the secondary position. And that's the major product. So that's the mechanism. Bromination forms three-membered ring bromonium ion. Strained bromonium ion will ring open to some extent, give a cation which is resonance stabilised. So there's some positive charge here, some positive charge there, and then the bromide can attack at both locations. And if it's a high temperature, it will favour giving the most thermodynamically stable product, which is this one. So the answer, you've got to answer this question: why is it the major isomer? So high temperature favours most stable product. Most stable product. Major product has less steric hindrance between bromines and more stable tetra substituted double bond. So the two things that make it more stable are less steric hindrance further away and tetra substituted double bond as opposed to tri-substituted double bond. So the alternative mechanism would be very similar to this, but instead of this ring opening to form a carbocation, it's really only a subtly different reaction, subtly different mechanism, where the Br minus comes directly and ring opens here, or it ring opens by attack there.